Current gives rise to a magnetic field. But is the opposite possible? Can a magnetic field give rise to a current? This was a thought which Michael Faraday had when he performed this experiment. This experiment consists of a coiled wire around a hollow tube, which is connected then to a galvanometer, which is a device to sense current. Faraday inserted a magnet into the coil, and he observed that the needle moved and it came back to zero again. When he pulled the magnet out, the needle moved again, but this time to the opposite direction. He tried moving the magnet faster, and he saw the deflection was greater. When he pulled out the magnet, the deflection was on the opposite side. When he repeated the experiment by moving the magnet slower, the deflection was lesser. What did Faraday conclude? He concluded changing magnetic field around a conductor induces a EMF. And the induced EMF is directly proportional to the rate of change of magnetic field. Lenz, on the other hand, gave us an understanding of what would be the direction of current due to this EMF. He proposed that a conductor will induce a current in order to oppose the change in magnetic field around itself. For instance, if we try to bring the north pole of this magnet near the conductor, it induces a current to produce its own north pole, hence cancelling the effect. If you try to pull the magnet away, it will induce a current such that a south pole is created, which would attract the north and prevent it from going away. A conductor induces current in a direction such as to resist the change in magnetic field. This is known as Lenz's law. The right-hand rule can help us find the direction of current in a conductor moving in a magnetic field. Just like Fleming's left hand, you stretch the fingers of your right hand 90 degrees to each other. If your thumb is pointing towards the direction of motion of the conductor, the finger points towards the direction of magnetic field. The middle finger will give you the direction of current. A direct application of Faraday's law of electromagnetic induction are generators. This is a setup of a DC motor, a coil with split rings present in magnetic field. But what would happen if instead of providing current, we were to manually turn the coil? If we keep Faraday's law of electromagnetic induction in mind, turning the coils will cut through the magnetic field lines. Hence, the coils will experience change in magnetic field. If we spin the coil, the arm facing north will move away from the north, which will induce a current in it in one direction. When it moves towards south and then starts moving away from the south, it will induce a current in the opposite direction. But because the split rings themselves keep changing direction every half cycle, the direction of current in the wire remains the same. And hence, this setup will work like a DC generator, where the current is flowing in one direction. On the other hand, if you want to produce AC current, you just need to replace the split rings with slip rings. Slip rings are ordinary rings which provide electrical contact and do not change the direction of current every half cycle. With such a setup, the current which is produced by alternating coil is alternating in nature, and hence it produces a current which keeps changing its direction every half cycle. This is an AC generator or alternator. If you change the magnetic field around a coil, a current will flow through the coil. But what would happen if you do that to a conductor which is a plane, like a sheet of metal? This induces a current which spirals within the metal. The energy in the current is lost in form of heat. This kind of current is known as eddy current. This is the principle behind induction heaters. Consider two coils, one connected to a battery with a switch and another connected to a current sensor. When you turn the battery on, the first coil has current flowing through it, which generates magnetic field. The second coil, which had no magnetic field, now experiences magnetic field, which is a change. Hence, it induces a current in it. When you switch the circuit off, the magnetic field goes away, which again induces a change, and hence a current flows. But what if you want a continuous current to flow? You need to replace the DC batteries with the AC source. This is the principle behind working of a wireless charger. Transformers. No, not these transformers. Let me explain to you what a transformer is. A transformer consists of an AC source of power supply, an iron core. The iron core has primary coil winding in one arm and secondary coil winding in the other. You connect the AC power supply to the primary. The alternating current produces an alternating magnetic field which magnetizes the iron core. Iron core carries this alternating magnetic field to the secondary coil, which in turn induces an EMF. Hence, just like in the principle of mutual inductance, without any physical contact, a current is induced in the secondary coil. The induced EMF depends on the number of turns on the coil. If the coils on the secondary are more than the coils on the primary, the voltage induced in the secondary coil will be greater than the primary. This is known as step-up transformer. If the coils on the secondary are less than the coils on the primary, the voltage induced will be less in the secondary compared to primary. This is step-down transformer. We can use the relation voltage at primary divided by voltage at secondary equals to number of turns in primary upon number of turns in secondary to design a transformer. Depending upon what is the input voltage and what output voltage you want, you can decide the number of turns in primary and secondary. A transformer is considered to be 100% efficient, which means power input equals to power output. Electrical power is given as voltage into current, which means V in equals to V out, I out. If the voltage at the secondary becomes higher compared to voltage in primary, the current in the secondary will become lower compared to current in primary. This is the trade-off which transformer has to do in order to step up or step down.